the vertices of the building of PGLD for any D, but you pay the price of moving to positive characteristics. And in this way you can present quotient of this building as Cayley graph, as the clique complex of the Cayley graph of this arithmetic lattice. So this will now sit in. Oh, I need to tell you the inner form. Never mind. So you need to find something which is analog to the quaternions. So they take a division algebra over a global field of positive characteristic, and they build a lattice which acts simply transitively on the vertices of the building. And then Lubotzky-Samuels-Vishne proved in I think 2005 that quotient by congruent subgroups are Ramanujan complexes. And they're of course Cayley. So they come from, they are the clique complexes of Cayley graphs on P, again, G, S, or something in between. So now we'll let's even do Q. So now it will be some Q to the L. And a lot goes into that. So I should say the fact that they are Ramanujan complexes uses a Laforgue solution of the Ramanujan conjecture in positive characteristic. It uses Badulesco work on the Jacques-Ellman correspondence in positive characteristic, which was only written 10 years after this paper. But they knew somebody would write it, so they said we're going to use that and let the expert fill in the details and complicated details. And Moglan-Valls-Fourget classification of discrete automorphic spectrum in positive characteristic to make sure it doesn't interfere with the Ramanujan-ness. So it's not trivial.
So sorry, what is SLV? Who is SLV?
Lubotzky, I don't need to write, Samuels, and Vishne. So I think
it's really lambda q to the L, right? The congruent subgroups.
Yeah, lambda q to the L. Yeah. Now you can't mix two primes as Francois told us. That's a pity. That's a price you pay. Okay, so I should give them credit, and that's the first explicit construction on Ramanujan complexes. There's another paper due to Ali Salveniaze, saying it right? It did similar construction.
And Cayley?
But nothing explicit, no Cayley. Right. Okay, now I want to show you how to take. Okay, so this is one direction. I'm just not going to go in it because I want to show you some other things. I want to take you back to LPS and see what else can we extract from it. You remember, I'm trying to say that for graphs are already high dimensional in the sense that there are edges, and we shouldn't ignore the edges. So the LPS lattice is the two congruent subgroup. It's the two congruent subgroup of gamma, where gamma is a Hamilton quaternion, invertible Hamilton quaternions over the center, where you put in Z 1 over P, and now you're adding congruent to 1 mod 2. And this is gamma. And as Francois mentioned in passing, the index of lambda in gamma, let me write it the other way, is 4. Francois said that, and where does this 4 come from? So I remind you from Alain's talk that without the 2, you get the solutions to integral quaternions with norm power of p. And Jacobi counted the solution and showed that it's 8 times p plus 1. But we only need p plus 1 elements because we're trying to get to the neighbors of a p plus 1 regular tree. So we have this extra 8. And Dalan said, oh, these are the 8 quaternions, the 8 quaternion group that plays around, gives us an extra symmetry of the solution. And that's true, but why is this only 4 and not 8?
Hmm? Are you asking me?
Yeah, because you probably get it faster and I want to fix it.
Because of the center.
Because of the center, yeah, precisely. In the 8th group you have ijk, which really gives you a different one, but plus minus 1 takes you to minus the same element, and we're working modulo the center all the time. Our building is a building of PGL, and our quaternions are modulo the center, so the plus minus 1 doesn't give us something new, it's the same element. But ijk gives us new things. And the point is, Jacobi was smart. He didn't put this 4 for nothing. It hints us that we should look deeper. Why are these 4 there? And now we're going to look at the tree of PGL2Q3, which is a 4 regular tree. So this is the, let's say, the origin. And now I can't really use directly LPS because LPS is word for P, which is 1 mod 4. So I'm going to use the Davidoff-Sarnak Valet generators. And I'll tell you, well, actually I'm going to do something else. I'm going to look at the element I plus j plus k. This element is purely imaginary, and a purely imaginary element always has its square in the center. In this case, its square is minus 3. Okay, so this, and minus 3 is trivial. It's in the center. We're modded out by the center. So this is an element of order 2, and actually if you check what it does, it flips this edge around. So alpha flips between these 2 vertices. And if you further check, you'll see that the extra symmetry will come from I, j, and k acting on the solution. Take this guy to these 3. So if this is alpha V0, this is I alpha V0, j alpha V0, and k alpha V0.
I'm wondering what happens for 5.
For
Q5.
With I, j, and k?
Yeah.
Play with it. I spent several months doing these games. It's fun. Really, it's like somebody, it really feels like somebody left all these extra symmetries for a purpose. They behave really nicely. So, what do I want to say? I want to say that from this you can really, okay, so here's an exercise. Finish what I started here and show that a gamma, sorry, I keep writing lambda, gamma acts simply transitively on the edges of the building of PGL2Q3. Now this, until now we had the general P, now this is gamma of, for P equals 3. But this means that I can now identify the edges of the tree with the elements of gamma. So what will happen if I take the Cayley graph of this gamma with respect to the following generating set? I'm going to take, I'll tell you what I want to do. I want to do non-backtracking walk. So I want to get to these 3 edges. How do I get to them? I first rotate. So if this is my first edge, I'm going to rotate it here and then flip by alpha. So I'll get one of these. So this is alpha E, alpha IE, this is alpha J, and this is alpha K. So I'm going to take the set, generating set alpha I, alpha J, and alpha K. Then I'm getting the graph whose vertices correspond to the directed edges of the tree, and its edges correspond to non-backtracking steps on these directed edges. What I really got is the directed graph of the non-backtracking random walk on the 4 regular tree as the equivalent of PGL to Q3. And now I can play the same game. Now take, let's call this X, maybe X is taken, so Z3Q to be the quotient of this thing, so the Cayley graph of gamma Q with the same relation. So this will be a Cayley graph on PGL or SL2 FQ with these 3 relations, and I'm going to get, what am I going to get? Well, this is the Cayley graph. First of all, it's not directed anymore because this set is not close to inverse. Right? If I can, the element that takes me from this edge to this edge, there's no element which takes me from here back to here. I organized my generating element to encode the non-backtracking walk, which is not invertible. So I'm getting a directed graph. It's a Cayley graph with a non-symmetric set of generators, so it's a directed graph, but it's Ramanujan. It's a Ramanujan digraph. The way to see it is, this is, okay, I think the simplest way to see it is that this is actually the digraph of non-backtracking walks on the LPS graph where you put gamma. This is the Ramanujan graph. And we know from Ihara that the non-backtracking graph of a Ramanujan graph is a Ramanujan digraph. So, this is a way to construct a Cayley Ramanujan digraph. Why do we care? People usually prefer symmetric graphs. So, I'm telling you, it's because they are wrong. This is really better. People prefer symmetric graphs because then the adjacent matrix is self-adjoint and you can do spectral analysis and everything is fine. But actually, in the non-symmetric world, you get better expansion. And simply because you don't have to go back. You don't have the inverse of an element. This is why now we can get from 2 square root of k minus 1 all the way down to square root of k. But the more fascinating thing is that this exists in high dimensions as well. Thank you. We have no idea how to give PGL3FQ a set of generators so that this will be a symmetric set of generations so that this will be a Ramanujan graph. But using these ideas, we can give it, using the geodesic flow on the building of PGL3, I can find a non-symmetric set of generations which will make this a Ramanujan digraph. So that's why I'm claiming that it's stronger than symmetric. Then the Ramanujan digraphs are better than Ramanujan graphs. Because of that, they're also harder to find. Notice that our construction only works for p equals 3. It's not like in the LPS that it works for all p congruent to 1 mod 4. So it makes sense. If it's something stronger, it should be harder to find these guys, and it is. Because you need now simply transitive action on edges, not on vertices. So you need denser lattices. And what happens if we do want to go to higher dimension? Then I need to switch somehow. How much time do I have?
At least 10 minutes, a bit more maybe.
Considering that we started like
more like 15
17 minutes late.
You have at least 15 minutes.
What happens if you want to continue with this to higher dimension? So, okay, one option that I said is go to characteristic 0, a positive characteristic, and start playing with division algebras. But if you want to stay with positive 0 characteristic, there are no division algebras after the quaternions. So your game ends unless you go to another group. So the idea is to go to unitary groups. So here is a unitary group over a ring R. So let's keep things simple. These are going to be all the matrices in GLD Ri that satisfy A star A equals the identity. Well, R is a commutative ring, and I means that you added a square root of -1. So this is what Ri means.
And GL meaning under the determinant is invertible in the ring.
It has to be,
Oh, it's that one. Okay.
right? GLD.
Yeah.
So this is the unitary group. I would like to say that this is what we need, but we actually want to look at something which is a bit bigger. We want to look at a generalized unitary group, which means that I can actually allow to A star A to be a scalar, not necessarily the identity matrix. And as always, we want to divide by the scalar. So this is modular scalar matrices. So this is the group we're going to work on. Here is one exercise for the field F. Show that the Hamilton quaternions over the center on F, over the center, are isomorphic to P, G, G, Q, F. So it's really a group that captures what we've been working on, but generalizes to higher dimensions. Nobody asked what happened if R already has a square root of -1. Is this because you know what happened?
But do you want to use the same definition, or do you just want like a?
What?
Do you just want a quadratic extension, or do you just?
Yeah, but what happens if I put here QP, where P is 1 mod 4, so it already had a square root of -1.
Nothing changes, right?
What?
You still get a quadratic metal extension of the...
A quadratic metal extension. Yeah, that's what I did. So the point is, you should have said, wait, but what if this is not? Because I didn't start with the field. If I would start with the field, I would be angry. Okay. You should have been angry, but you didn't. So here is the second exercise. If R already has a square root of -1, then your group is actually PGL. You can write an explicit isomorphism using this guy. So we're going to take that. So now we're going to fix Q. We're going to look at QP, where P is 1 mod 4, so we're going to have this. And then gamma, which is PGU, okay, I'm going to write G for PGU, D. And then gamma, which is G V1 over P, sits as a lattice, as a co-compact lattice in GR plus GQP. Now, GR is simply what we know as the projective unitary group in T variables, because I added I, so I got complex numbers and I got the standard unitaries. And this thing we just said is isomorphic PGL, DQP. Because this is compact, I can also project. That's I can kill this factor because it's compact, and I got a lattice in PGL DQP. So I ruined Francois' exercise for you, but such is life. I need it for what we want to do now. And the point is, you can play the game, the Lubotzky-Phillips-Sarnak game in higher dimension, and that's what we've been doing for some time now, looking for sublattices which act simply transitively on the vertices or edges of the building. So here's the first example we had. So this is a joint with Shai. You're going to take so if you remember in the LPS, you took the S-arithmetic subgroup and you went to the second congruent subgroup and you get something that acts simply transitively. It's not that simple, so you need to tweak things until you find something that works. And what we found here is you take all the gamma in 1 PGU 3, the 1 over T, that satisfy this mod 2 plus 2i. And this acts simply transitively on the vertices of the building of PGL3. QP. The weird thing here, the hardest part is to show that this is a group. Because it's really not apparent why should this condition be closed under multiplication. And it's just like half a page of verifying it. And I think Shai presented this work at the IAS, and this was the part that Delin was most curious about. Like, what is this group? Where does it come from? And we had no clever idea. We just sent him the proof and he read it and said, oh. I think he hoped that it would come from some deep geometric insight, but we have none.
But how did you get to mod 2 plus 2i?
Many failed attempts. We just tried a lot of things. What?
You just decided to find mod some.
The game is you start with the largest lattice you have, you verify that it acts transitively, and then you start imposing congruence condition. And if you went too deep, it stopped being transitive. If you went too shallow, it's still not simply transitive, and you hope you'll get something which does both. And once you have this thing, you can quotient again by, now this gives quotient, let's say arithmetic quotient of the building mod congruence group Cayley. A Cayley structure. So, okay, maybe I'll show some examples.
So there is a classification of
Sorry?
there is a classification of simply transitive lattices on transitive buildings, but it's in rank 1 higher.
Just a second. Say. I know that in rank 5 and higher there's Ali Reza, Salehi, Golsefidi, and Mohammadi. So I asked them when I started this, and they say, no, we low dimension are a mess. We have no idea what happened there. So we work by hand. There are no such lattices in rank 12 and above.
9 and above.
9 and above it ends. So this is just low dimension miracles. So here is, so these are Cayley graphs on finite group that we get from our lattice, from our arithmetic lattice. And I just should be telling you what is the operator whose spectrum you are seeing. There are many geometric operators. Here we studied the operator A1, which acts on functions on vertices. Was it mentioned at some point? So what it does, A1 takes a function on the vertices, and it's not the adjacency operator, not the entire adjacency operator. You take the neighbors, but only the neighbors whose color is the color of v plus 1. So if you're a vector of color 0, you take the neighbor of color 1, from color 1 you take color 2 you take color 0. And the same thing with A2 would be neighbors of color v plus 2. If you add them together, you get the adjacency operator. But the point is, because the Hecke algebra is larger, there are more operators you can look at. And there's a clear advantage of A1 over the adjacency that you can see here. It's complex. It has complex spectrum. The adjacency is self-adjoint, so its spectrum is real. So you get boring pictures of dots clustered on a line. But once you go to complex operator, you get to non-normal operator. No, to non-self-adjoint operator, you get beautiful pictures. So.
Sorry, I don't understand. What are the dots? What am I looking at?
Spectrum. So we have this geometric operator on the building of PGL 3.
Right. So the picture
So-
is what the spectrum.
First, the red triangle is the continuous spectrum of this operator on the building. The building is infinite. The
So I'm
spectrum
looking at C, the complex number. I'm looking at the complex numbers. The subset of C
of what?
of the complex numbers.
Yes.
Yeah. These are the complex numbers. Yes, these are the complex numbers, and the red is the spectrum of this operator on the building, and this appears in many works. A lot of people drew this nice picture of this triangle. What is the spectrum on the building? It's some polynomial in the Satake parameters, polynomials of modulus 1, but what you see in blue are the eigenvalues of a Cayley graph, which is obtained as an arithmetic quotient of this building using this lattice. So you take this lattice, mod out by a congruence lattice. By strong approximation, you get a finite classical group. You take the projection of your generating set, and this set was chosen so it takes you to the A1 neighbors. So maybe I should say, now we take we're going to take this lattice and take the not the S which take you to all the neighbors, only the S that take you to the neighbors of color 1. And we get a finite Cayley graph, and this is the spectrum of this finite Cayley graph, and the whole point is that the spectrum is within the spectrum of the building. That's the Ramanujan. I threw out the trivial eigenvalue, because it's much further away. So just not to ruin the picture.
You didn't throw anything else.
No.
Okay.
I think both of them are, yeah, there are no, the only trivial eigenvalue is the trivial now. There are no other trivials. I was very excited when I first did that because I knew that's what should happen, but when you actually program everything and construct the graph and compute the spectrum, and these are enormous graphs, by the way. The PSL 3.5 is already 300,000 vertices, so your computer needs to run for like 2 weeks to compute the spectrum, then you plot it, and it's inside the building spectrum. I was very excited because you hope you understood all the Langland thing correctly, but to get a verification is very reassuring. And then, how much time do I have?
1-2 minutes.
1-2 minutes. And then people, and very clever people, told me, no, you're making a mistake. Ramanujan doesn't hold in higher dimensions. That is known since the 80s, that there are functorial endoscopic leaves, theta function, Navi, Tetetsky-Shapiro. You're only looking at small example, that's why it seems Ramanujan, but you'll add more vertices and it will stop being Ramanujan. And I added more and more vertices, I got to 15 million vertices, and it was still Ramanujan, and at that point Sarnak told me, okay, now you need to find out why it is Ramanujan. So we spent like 4 years to show that we were lucky. Our lattice managed to avoid the failure of the naive Ramanujan conjecture. So it's known that the naive Ramanujan conjecture fails, and we were just lucky to not step on any of these bad automorphic, non-cuspidal automorphic forms. But in more recent work with Brooke Fagan and Kathleen Moreshat, we constructed another simply transitive lattice which doesn't do that, which doesn't avoid. And I was even happier for some reason to see that they were also right that the naive Ramanujan conjecture failed. So these are quotient of another simply transitive lattice, and coming from the Eisenstein field, Q minus square root of 3. Square root of minus 3. And you see the Ramanujan spectrum in blue. And you see this red part, this is the part that corresponds to non-cuspidal representation in the automorphic spectrum, which are non-Ramanujan, and there are points on this. There are points. And actually proving that, okay, you can do that by hand, by computer, plotting some example, but it was really, really hard work to show that you continue getting these bad eigenvalues for all Q. So we can get, once you go to high dimension, you get Ramanujan, you get non-Ramanujan, the story becomes more complicated. You need to engineer things well. And proving anything in this world is really complicated. So we had no idea, but proving that our complexes were Ramanujan was not, it turns out it was not impossible before and Go proved the fundamental lemma, and people use that to prove Ramanujan for self-dual cohomological representation. So we've used everything that number theory has to offer. Like we came in the right moment when they had the tools ready. 10 years earlier, we couldn't do anything. And last thing I want to show you is what I promised earlier. These are the Cayley Ramanujan digraphs coming from the construction that I showed you with the extra 4 I, J, and K acting on the edges of the Q3 tree.
What does that say? PSL2F what?
It's 31. I just took my favorite Q. It was 31. Now you know it. And this is the quotient of the the lattice that acts simply transitively on directed edges with a generator that encodes non-backtracking walk, modulus 31. And you see here the Ihara spectrum. So here is the trivial eigenvalue, and these are the eigenvalue on the square root of the degree, and here are the plus minus 1 coming from the cycles. And this is the same thing done for geodesic flow in PGL3. So this is a Ramanujan digraph on PGL3 coming from geodesic flow on the PGL3 building. I think that my time is up, right? Oh, I have 2 minutes. I just want to say that one thing I'm a bit sad that I didn't have the time to come to, and the fact that this thing embeds in PU3R gives a completely new story of expansion, of how well these matrices spread in the compact unitary group. And this is called, so Peter Sarnak tried to coin the name Golden Gates. He always said that Ramanujan graphs caught so well because of the exotic name they gave them. And he wanted to say that these matrices, when you put them in the compact group, they also have optimal expansion. And gates come from the fact that they can be used as unitary gates in quantum computation. This is why you want to approximate elements in the unitary group using a generating set that you understand well. And you can prove such things, and for that you actually need to use the full power of the Lin theorem, not only the version of Eichler. So for the expert I will say that for Ramanujan graph we use Eichler, which is the Ramanujan conjecture for automorphic functions of weight 2, and for optimal expansion here you need the Lin, which gives you the Ramanujan conjecture for all weights that appears here as the spherical harmonies. I hope I managed to intrigue somebody. I would like to thank the speakers, the organizer for the speaker and the organizer for an amazing week. I had tremendous fun here and outside. Thank you very much.
Thank you very much. Maybe first ask if there are some questions about the lecture, and then say some more. Yeah.
So what is exactly the expansion result you get for this specific lambda? Do you get high-dimensional expansion?
You get whatever you know to get for Ramanujan complexes of high dimension. So it all depends which operators you take. If you take collision free operators, then you know you'll get Ramanujan digraph, so the spectral gap, the second eigenvalue will be the square root of the first one. But you can take other operators and then compute what you get. It's always fun to find yourself start playing with McDonald polynomials, and you find yourself going again and again to McDonald book.
But so for this one, everything works.
For this, yeah.
Other questions? Tot let's first thank Ori again for his beautiful lecture. Yeah, and to end, I would like to add some more words of thanks, in fact. I mean, first of all,